Hello everyone, this is Dr. Indradeep Kumar, Assistant Professor IARE, Hyderabad. So in this video, we will see torsion of an arbitrary section B. So our lecture topic will be torsion of an arbitrary section beam. So in an arbitrary section beam, how the torsion will be there, that we will see the derivation first. Like after that, how the torsion will be there, and then we will see in next videos, like based on the numerical of that one, how we can use this theory in the numerical to find the torsion. So in this video, we will see the derivation first. So let's see here. That is for open section. So you can see in the image that open section is, that is from here, this side, that is open. So this is not up this side only. This is throughout the length from here to here, that this part is open. Right. So it's simply just like any cylinder is there and you are simply cutting, and now this is there. So this from here to here, this is the total one that we have to take. So from where this concept arises. So that's why the theory originally developed by Wenger and Kapos, in most generally known as Wenger's torsion bending theory. So this theory is named as what? Wagner torsion bending theory. Okay. It assumes, so according to Wagner assumes that the beam is long compared to its cross-sectional dimension. Just this dimension, whatever is there, compared to that dimension, this length of the beam should be very long. Okay, not in the same order. Like suppose this is the dimension, the cross section of this one, and this is the size of the beam. No, not this one. So if this is the cross section, this beam should be like very long. Okay. So with its cross sectional dimension, that the cross section remains undistorted by the loading, and that the shear strain, that gamma ZS of the middle plane of the beam is negligible through the stresses produced in the shear strain. So why? So the shear, that the cross section remains undistorted. Means cross section, this should not get like open is there. So if you will suppose apply the force here, this will get what happen? It will get twisted or anywhere. Right. So that should not get twisted. Means that should not get undistorted by the loading, and that the shear strain, that gamma ZS of the middle plane of the beam. So middle plane is this one here. Thus you can see that Z. That's why here it's Z is there, gamma Z along the surface. That should not again. Okay, the beam negligible through, so this gamma strain also should be negligible through the stresses producing the shear strain. Okay, from similar assumptions is derived in section. This one I just mentioned because if you have already, because some concept I use that here, but everything we cannot cover in the same thing, right? So this you can refer this 18.2 point section from the Maxon book. Okay, there you will get the derivation of this one, because for deriving we require this one, but we cannot derive again. For deriving, then one video itself will be too long. Deriving again, how that wrapping this W will be this things. So simply I mentioned that here, there you can see in the section 18.2.1 how that Maxon derived this W value, that is wrapping value. So simply directly, that means directly we will use here in our derivation. Okay, so you can just refer 18.2.1. An expression for the primary wrapping W of the beam. So this W is the wrapping. So anything we are wrapping, then what happens? Just like if pack is there. So first we are putting the cover. Okay, then we are folding that also all the side, right? So in all the side, how much that wrapping is required, that will see here. So that is the wrapping, that is minus of 2AR d theta by dz. Okay. So this is our figure on which we have to, so just see along the Z axis, the torsion T is acting. So at this shear load, that is open section, that there is no distortion already. We had seen that somewhere here undistorted. So at that point S is 0, but all along the surface S is acting. So only on this surface, right here on the edge of this one, right there S is 0. After that remaining here, that S is there. Okay, so torsion of an open section beam fully built in at one end. So fully built in at one end. That is, so this is a diagram of open section, the torsion for open section. In the presence of axial constraint, d theta by dz is no longer constant. So axial constraint is there because we have seen that mid plane we are using. right? If we will not use, then the torsion will be there. And earlier also we had seen that for the torsion, that force must act through the shear center. Then only no torsion will be there. If other places like other than the shear center, if you will apply the load, then some torsion will be there. So at the shear center only the torsion will be 0. So same here. Why? Because of that axial constraint is then that force should apply at the what origin or center only, that shear center, then only no distortion will be there. But we are not applying, means d theta by dz, now it won't remains constant, right? So is no longer constant. So that longitudinal strain del w by del z is not 0. Now earlier what we have taken, hence d theta by dz is 0 means there is no constraint. No constraint means no strain. So longitudinal strain we have taken that as 0. But here d theta by dz itself is not constant, means del w by del z also it won't be 0, right? So it's not 0 and direct, and also shear stresses are induced, means here direct and shear stresses both will be there, right? What then? Sigma tau, okay, is E del w by del z. So here del w by del z also is not a constant. Just put the value of that one. So del w by del z, just now we had seen here, w is this one. So just differentiate this one. So del w, right, del w by del z equals to, because minus 2ar is constant, so that will be minus 2ar, and d theta becomes what? d2 theta by dz square. So just dw by dz, substitute here. So just after substituting minus 2ar, that value E is there, and for del w by del z is d2 theta by dz square. So from after differentiating the w value, so you got this one. So this is sigma tau, that is our first equation. The sigma tau stress system must be self-equilibrating, since the applied load is a pure torque. Why? Self-equilibrating means they should come to the equilibrium by themselves. Why? Because only the pure torque is applied. No other loads are there. No other twisting are there. Only pure load is considering we are. Therefore, at any section, the resultant in the load is 0. Here, the no load, no, that is because of pure torque, means what? At the intersection, load will be 0. Hence, just apply that one. So at equilibrium or for equilibrium, for the C, right, sigma T into TDS, that area, that force should be sigma T is the stress into area, will give you the force. So force must be 0, means this one, sigma T into area, that is TDS equals to 0. Close circular C, that integral of C denotes integration around the beam section. So this C set around the beam section, that here means this force around the beam section will be equals to 0. Or from equation 1, from this equation, just integrate it. So 2ar TDS, the closed integral of 2ar TDS is equals to 0. Why? Because sigma T is here. This one we have, right? So after putting this equals to 0, that is the second equation. The limits of integration of equation 2 for this one present some difficulties in that AR is 0 when W is 0 at the known value of S. Means just here, present some difficulty. What is the difficulty? That AR is 0 when W, when wrapping is 0 means AR is 0. So what will be that time the limit? At an unknown value of S. Though even S is unknown, then also AR is 0 when W is 0. But that should not be there. And for S should be known or that constant. So even S is not there, that load is not there, then also AR is 0 means that what wrapping also will be 0. So that's why choosing this one limit is here somewhat difficult. Now that what we are substituting here, this 2AR, let's find for that one. Okay, so let 2AR that we are finding. So just see from the figure. The same figure we will use in the numerical also. So remember this figure we will use finding the twist. Okay, that also the angle of twist, how much that will be there, that will be here. That we will find by using the same diagram. So I am explaining this diagram first here. Then we will see to find the angle of twist also. That's why you see here it's the return center of twist, that is R. And this total angle is what? Angle of twist. So here you can see S is equals to 0 as you move. That means from the beginning of this one. Okay, that goes from here. Right, now just see here, you can see this one first, like, okay, also curve is, okay, So this is center, right, from here to here. This is the total S. So S is equals to 0 here. Here is A. Now this two, what we have to find, that AR. Okay, so AR is this one. So just see here, from here, this is total is AR, right, this one. AR dash is half of this, you can see this one, not half exactly, but this one, R not, because S is 0 at that time, and here wrapping is 0. So you just see here, 2AR not, that not is for the S, when S is 0 means that wrapping is 0. So that is how. So from here, this is like this. Okay, so means overall from this part, if we will subtract this part, we will get this part, right, and that is only our AR, right. So this whole, this part only from here to here is our AR, right. This part is AR dash. So, and this total is 2AR naught. So what we drew, this total is what, 2AR comma 0 for S equals to 0 to S, minus, if we will subtract this part, right, we will get this part, right. So this part is what, A dash R. So 2A dash R, right, that you will get this one, that is 2AR. Clear? Where AR naught is the area swept out from S equals to 0, and AR dash is the value of AR naught 0 at W equals to 0. So AR naught is when what, A dash R swept, that is at 0 wrapping. So when W is 0, that's why here it's 0. And previous also we had seen, at that time W wrapping will be 0. So that's why choosing limit is difficult. Now just integrate both the side. Okay. Then in equation, so from figure 2, right, from this figure, AR value is 0. Then in equation 2, just substitute here from equation 2, just see here, angle 2AR TDS equals to 0. So now put AR value here. AR value, this AR value here, right, or 2AR is given already. So 2AR, for directly 2AR, you can take this whole value. So now that equation becomes what? Here, that is given as integral of C 2AR TDS, right? So 2AR, we can put that one and into TD, right, TDS, right. So just see here, those two values into TDS, this 2AR naught minus TDS, just separated, minus 2AR dash, that is this one, because it's a constant, close integral TDS, that must be equals to 0. So simply 2AR value substituted where? Here. Okay. So now with negative sign is there, hence we got that integral equation, that 2 integral with negative sign. Right. Now take this whole thing to this side. Okay. So after taking, what we will get? Close it, let's see, 2AR comma 0 or R naught T into DS, that is equals to what? This after taking this side, 2A dash R C of T DS, right, after taking this side. So now what we have to find, that 2AR dash. So 2AR dash will this side, and then this will get divided this side. So integral of 2AR naught TDS by integral of TDS. Just see here. Now one more thing, don't cancel simply this integral TDS and integral TDS, because here 2AR is not constant. If it's a constant, then we can take out of the integral like this and we can cancel, but that 2AR is not constant, right? This AR part is not constant. That depends on what, where this W will be 0. That W can be 0 here also, so that time AR will be this total. Okay, if W is 0 here, then AR will be this much part only. So that AR is not constant. So we cannot take out of integral, means the whole integral should be there. So don't cancel, okay, TDS out, integral of TDS, we are cancelling. No, that you cannot. Giving 2AR equals to 2AR naught minus this one, because this is 2AR, right? Just substitute here. After getting 2AR dash, right, substitute in this equation. So after that, what you will get, 2AR equals to 2AR naught minus this integral part, right? So let's see, you are giving 2AR equals to 2AR naught minus this whole thing as 2AR dash, right? So this is 2AR dash, that is 2AR becomes 2AR comma 0 minus integral of C 2AR comma 0 or R naught TDS by integral of C, T, D, S. So this will be the value of 2AR, right? This area. The axial constraint shear flow system Q is in equilibrium with the self-equilibrating direct stress system that already we had seen. That should be self because no other forces is acting. Thus, from equation 2, right? Del Q tau by del ds, del S plus T del sigma T by del Z equals to 0. So just see from the equation 2. Right? Here. Right. So just after differentiating, you will get this one. So del is 0. Hence, now take this to this side. Hence, del Q tau by del S is equals to minus T del sigma T by tau by del Z. Substituting for, this is 4 here. R is missing. 4 sigma T from equation 1. Now just here, substitute this value. Already we found in equation 1 that you can see sigma 1. So this is. Let's substitute this value there. Right here. So that will be del Q tau by del S equals to minus T into del of that whole value divided by del Z. Right. And noting that what that Q T is equals to 0 when S is 0. That already we use. So when S is 0, this also will be 0. Okay. So now that Q T becomes from where to where? 0 to S, 2AR ET dq theta by dzq into ds. What? After substituting here. Right? So we can just see what happened. Del Q tau by del S equals to minus T into, what is sigma T? So see here. Sigma T is minus 2ARE minus 2ARE into d2 theta by dz square. That is right. So it's minus 2ARE into d2 theta by dz square. That we use. So now this minus becomes plus. Okay. So now after this what we can say 2ART and then divided by dz. So with respect to dz we are differentiating. So this becomes T into 2ARE, and after differentiating this becomes what? Already second derivative is there. So that will be becomes the third derivative. So this is d3 theta by dzq. Okay. So that is here. And this ds was here. So that ds came here. So this del q tau is equals to 0 to s 2ARET dq theta by dzq into ds, or right. So this is what constant. Already we had seen that d theta is constant. So either d theta by dz is constant means dq theta by dz or dq theta by dz also constant. That e is also constant. So take out that one from the integration. So e dq theta by dzq into ds is out of the integration. That is here. 0 to s. Now what is left here? 2AR, then t and ds. So 2AR into t ds. Right. So that will be the value of q tau. Okay. So this is the fourth equation. Now similarly for t tau, in the same way we can write. So close integral of p r into q tau ds. The torsion load into perpendicular distance. Right. So that will be here. So this is what? The stress, that's here, and this is what? Area, that will give you the load, and into distance will give you what? The torsion. Right. So that formula. Substituting 4 in 5. So just see here, 4 in 5. Substitute here at q tau. So what we will get? T equals to C P R. Okay. Q tau is this one. This whole thing into, okay, E dq theta by dz q close integral of this whole thing inside this one. 2AR T ds, this bracket close, okay, into ds after substitution. For this we substituted this one. So this is our q tau. Okay. So after substituting, you see here that PR is constant. So that PR into this value, they have taken already DE. dq theta by dzq as constant, okay, into ds. The integral in this equation is evaluated by substituting PR equals to d by ds, that is differentiation of 2AR with respect to ds. This is this one only, right? Just I wrote in linear way, but this is this one, d by ds of 2AR, and integrating by parts. Now after this, just apply the integration by parts. So here d of ds, that is PR. So this into substituting here this. So this into this, now two word is there. That means what we have to do? Product rule. So in integration, product rule is by parts. So with by parts, we can integrate. So after integrate, what we will get? 2AR close into that first integral minus second integral into, so that just same in that by parts formula, 0 to s 2AR t ds, that minus 3 4a square r t ds. Okay, so this will be the after integrating this one. At each open edge of the beam q tau, and therefore 0 to s 2AR TDS is 0 at each open edge. So at each open edge, what will be there? This term will be 0. Okay, yeah, so that the integral reduces to what? Minus c 4a square r TDS. So means this 0 to s 2AR TDS, this is 0. Right, so this is 0 is 0 into this 0. So whole this term will be 0. What is left? Only this term. Right, so that term is here, is giving this one. So that's why now just substitute this, will what you will get, because we solve for this part only. This is here, right? So we are solving, and before this, what is the E dq z by dq? So just here finally we will get theta equals to minus E tau r d theta by dz q. Why? Because this is the tau r value what we got here. Okay, so finally we got tau equals to minus E tau r dq theta by dz q. So just in question what they will do, you can see if you will the question, they may ask to find the total torque, okay, or to derive this one. They will give you this value itself and to derive for the open section beam of our arbitrary. So that can be changed, that can be find anywhere. Like they can ask for this one, tau t only you are finding. So in this, what we have found here, this qt, they may ask to find, they will put this question, derive this one, right? So anyway, wherever the importance are there in between in exam, they can give anywhere that value, and up to that you have to proceed. So from this equation itself, 3 to 4 question can be found, right? So make sure to go through line by line and whatever the step they mentioned, right? With the same figure, later we will see we can find the angle of twist. So again, this figure we will use to find the angle of twist. The same procedure will be there, only the d theta by dz we have to find. So this is very important for solving next 3 to 4 question, these concepts. So make sure to thorough with this one. Okay. Okay. So now after where tau r is what? In of c, that integral of c 4a square r TDS, the torsion bending constant. So this TR is what? Torsion bending constant, and is purely a function of the geometry of the cross section. So how the geometry is there? If it's a circular cross section, that cross section, rectangular, triangular, or whatever their cross section is, their geometry of that cross section, that depends on that only. Why? Because AR is here. Okay, the total torque T, that was the total torque T, which is the sum of St-Venant torque and Wagner. So St-Venant torque already we had seen, that is, this is the St-Venant torque, right? And then Wagner torsion bending. So this is the sum of these two. But what we got, that Wagner torsion is minus of E tau r dq theta by dz q. Hence after substituting, we will get this one. So this will be the total final torsion. Okay. So now just see here in this also, this is the question according to this one. This is the question to derive. But it's not necessary. They can ask you up to this also to derive, or this whole thing, or as I mentioned, up to this also that you need to derive. So first see the question, read the properly what exactly they are asking, and then proceed according to that one. So with this itself, 3-4 derivation can be formed and numericals also. right? So that's why this is very important PPT. Okay. So now just let me recall quickly. Okay. So now this is what open section beam is there. In that we have to find the torsion. That question is, an open section beam, simply find the torsion. So from where we started, that wrapping, right? Wrapping, we used how this equation we got already, I mentioned here. Like in Maxian book, if you will see that 18.2.1, there you can see how they derived, and they got the wrapping as equals to minus 2AR d theta by dz. Okay, so here we are not deriving that one, simply that use that one. So, and that also is there, that is passing through the mid plane of that one. So right here, that is there, that's why that is that, and torsion. So at this, what is that? At this side, this open, that is equals to 0, or along the surface, that as is acting. Right. So for this, we have to find what? The torsion equation. Okay. So what we did, we started from what? That it's a given d theta by dz is not constant. So if it's not constant, means del w by del z also is not 0. Hence sigma tau is equals to E del w by del z. So del w by del z, for that w is here. Differentiate this one. Right, and substitute here. After differentiating, substitute here. So after substituting, we will get this one that I already showed you how to differentiate. Right, and that also is mentioned. Sigma t is what? It's a self-equilibrating. Means they should come to self-equilibrium. No other extra force will apply on that one. Why? Because there only pure torque is there. So hence pure torque is there, means no other forces are there. So whatever the equilibrium condition will be there, means what? Total force acting must be equals to 0. So here that is there. This is sigma into area is force. So that is TDS is area. So means this total force acting at the what? Beam section is 0. So what is that C for the beam section? Okay. Now, so from equation 1, what we got? d2 theta by dz square is a function of z only. So just here, no other things are there. Right. So from there, close integral of 2AR ds. Just after substituting, that also must be equals to 0. Now here, what is that? Finding limit of this integral is difficult. Why? Because this AR is not 0. If AR is 0, then it's okay. But AR is not 0 when wrapping is 0. So when wrapping is there, then also AR will have some value. So first we have to find that AR value. After finding AR value, we can substitute here, and then we can integrate for the entire beam section. So how to find AR? Let's see. So for that only, this is there, that is called the twisting, that computation of swept area AR, how to find. So this from here, when S is 0, it reaches to S, that total is what? 2AR naught. Why? Because that time W is 0, that wrapping is 0 in that case. So that's why just it's mentioned 2AR naught, when not defined here, when wrapping is 0. Okay. So for that, so this whole part is this one, and 2, that is AR dash. AR dash is this part, right? This part. So what is left? This part only is left, right? So that will be what? This whole minus this one will give you this one. So that only is the, right? This whole minus this part is giving what? This part, right? That is 2AR. So this part only is our 2AR, where AR naught is the area swept out from S equals to 0, and AR dash is AR when wrapping is 0. So just substitute here, take integral of this one. So 2AR, 0, TDS minus 2A dash. So after, so then from equation 2. So just substitute 2AR, this value, where? Here. Right, after this, we got this equation. From there, just take this to this side, find 2AR dash. Once you have 2AR dash, substitute back here, then you will get 2AR dash. So this is a 2AR dash equation, so 2AR equation. Okay, after that, from again equation 3, del Q tau by del S plus T del sigma tau by del Z equals to 0. So this is there, take this to this side, so this becomes negative. Now already we found that sigma T, substitute that value here, that I showed you here. After substituting, you will get this one. Why? Because then that is in terms of, and then again after substituting you have to differentiate. So that d2 theta by dz square was there, so now that becomes what? d3 theta by dz cube. Now next condition is what? When noting that q tau is 0, when s is 0. We have, just substitute this and let's see. So q tau 0 to s 2 RET dq theta by dzq into ds. Or simply for that we can write that just take these things constant, each constant, this is constant, so what is left inside? 2AR T ds. So 2AR T ds. Now, so this is for q tau. Now this is for torque, that is CR1. That's it. This is for torsion. So PR into q tau ds. Now here we have to put this q tau. So for just see, for finding this torque, right? This torque, what we are finding means here, which one is there? Let's see here. That Wagner torsion, right? So for finding Wagner torsion, what we required? Q tau. For that only we found here this q tau. So just to mention here, we found this one. But if suppose numerical is there, then it's not required to derive everything and then substitute the value. Simply you can write that q tau. We know that q tau is this much. Then write PR into, replace this q tau to this whole thing into ds, and then put the value and integrate it. Right. So after substituting this, what we will get? Let's see here. So substituting 4 in 5, we will get this one. Okay. The integral in this equation is evaluated by substituting what? PR equals to d by 2AR of ds. After that, what is there? That will be 0. So at each open edge beam, q tau, and therefore, right, 0 to s, this 2AR ds is 0. So once this is 0, this whole term will be what? 0. So what is left? Only this term. What is left? Minus c 4a square, but 4ra square tds gives what? Just here, t tau e tau r dq theta by dz cube. So 1 is here. Now we have to find where tau r is what? That c 4a square r tds, the torsion bending constant. So this value will be constant. Okay. Why? Because it's a purely function of geometry of cross section. So it's totally dependent on geometry. So now the total torque will be what? That is the sum of what? Venant torque and Wagner torque. So here tau is Venant torque and Wagner torque, sum of these two. So this will be the total torsion equation or total torque, you can say. Okay. So if you have, just as I mentioned, that 18.2.1, so you can refer from the Mixon book to see the derivation. If you think that no, I should know the derivation also, then you can just refer that one. And if you have doubt any in this one, you just let me know. Okay, so that I can, or you just can comment on the video itself so that I can answer or I can resolve your queries. Okay, thank you.
Like, share and subscribe. Hit the bell icon for more updates.